Welcome students to the series of lectures on statistics. So far, we have been discussing probability distribution. We began with discrete probability distribution and completed the discussion of discrete probability distribution and moved into continuous probability distribution. And within continuous distribution, we have already covered uniform distribution. And now we have started one of the most important topic in all of these statistics, the normal distribution. In the last lecture, we discussed the properties of normal distribution and the application of normal distribution in CFA and FRM curriculum. But today, we address a deeper and a more fundamental question, that is, why does normal distribution appears everywhere? Think about it carefully. If you try to plot the probability distribution of, say, height of people in India, after a certain period, you will find that it is following normal distribution. If you plot like stock return or portfolio return, to be more precise, it will start following normal distribution. So again and again, you see the same bell-shaped curve. You see the same bell-shaped curve is appearing again and again. The question is why? The question is why? See, the intuition is very simple. Whenever you deal with a large number which are ID in nature, which is random in nature, the outcome tends to follow normal distribution. But if you see properly, this is just an intuition. And statisticians and mathematicians were not satisfied with this intuition. What they wanted a formal explanation, just like we explain rain through like evaporation and then condensation, forming of the cloud, and there would be a rain. The same way, they want to formulate it. Can we mathematically prove why normal distribution emerges everywhere? And in trying to answer this question, they reach to one of the most powerful result in statistics that falls under the umbrella of law of large number, that is central limit theorem. Okay, central limit theorem. Now this theorem provides a formulated reason why normal distribution appears so frequently in the real world. Now, a very important point that you would see different version of central limit theorem. There are multiple formulation of central limit theorem. Some are more general and theoretical, some are more simplified and practical. So in today's lecture, we'll first understand version 1, which is the most general and foundational form of central limit theorem. And this give you the true essence of the normal distribution or the reason behind the normal distribution. And once you understood version 1, then only we'll move into version 2 of central limit theorem, which you expect in your CFA and FRM examination, or which is present in your curriculum. Version 2 you will read in your curriculum. So let's begin with the core idea behind the central limit theorem. So let's read version 1. So version 1 says that the sum or average of the outcome, the sum or average of outcomes of the ID variables tends to normality as n increases, n greater than 30. Now, there are a few important things that you have to notice in this version of central limit theorem. The first is you need IID variable. First, you need IID variable. This is critical. If you're dealing with ID variable, then only you will see normal distribution. What you need? ID variable. The second is you just don't need ID variable. You also need the sum or average of outcome of ID variable. So not only ID variable, you have to play with sum or average. Then only you will see normal distribution. And if you have these two conditions met, then the third condition is that if the number of ID variable is greater than 30, the number of ID variable you're playing with greater than 30, then the sum or average of ID variable outcome will become normal distribution or tends to normal distribution. This is what it is. Okay. So what do we need? So we need ID variable, we need the sum or average of ID variables, and we need the entity, the number of entity greater than 30. Okay. So let's take one ID variable. So the ID variable that we have taken is the roll of a dice, the outcome of roll of a dice. Why it is ID? It is ID because it is independent and identical. The outcomes of the roll of the dice, which is 1, 2, 3, 4, 5, 6, are independent and identical. Why it is independent? It is independent because the probability of 1 as an outcome is not dependent upon whether 2 appeared on the dice previously or not, whether 3 appeared previously or not, or whether 4 appeared previously or not. So 1 as an outcome is independent, is not dependent on 2, 2 is not dependent on 3, 3 is not dependent on 4, 4 is not dependent on 5, so on and so forth. So all the outcomes are independent. So independent. So what IID stands for? Independent and identical. So we covered independent. What about identical? And why identical? Why the roll of the dice is identical? Because we are talking about the roll of a dice. We're not talking about a roll of a dice and a toss of a coin. And because of that, the probability of every outcome, whether it is 1, 2, 3, 4, 5, 6, is what? 1 by 6. How come 1 by 6? What is the probability formula? The number of outcome in the favor, divided by total number of outcome. What is the total number of outcome? If I want to know what is the probability of 1, it is 6 because it has 6 faces. What is the number of outcome in favor of 1? It is only 1 because one face has 1. So 1 by 6, same for 2, same for 3, same for 4. So the roll of dice is independent and identical because the probability of the outcomes are identical and the probability of each outcome are independent. Okay, so the outcomes are ID perfect. Now what? Now let's plot the probability. And we know that the probability is 1, 2, 3, 4, 5, 6. For 1, 2, 3, 4, 5, 6 is what? 1 by 6. So I will plot them. So I have my y-axis and x-axis. Okay. And I want to plot the probability of 1, 2, 3, 4, 5, and 6. Each one of them is going to be 1 by 6, 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 right? Or you can also plot it through histogram. Okay. Now, each probability, if you see this distribution, when you plot it, then the probability distribution does not look like normal distribution. It doesn't look like normal distribution. It doesn't have any bell curve. Okay. It doesn't look like normal distribution. It looks like a uniform continuous distribution. It looks like uniform discrete distribution, not continuous distribution. Uniform discrete distribution. Why uniform? Because the probability of every outcome is 1 by 6. So uniform. 1 by 6, 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 1 by 6. Okay. And it is discrete. It is not continuous. It is 1, 2, 3, 4, 5, 6. It is countable and finite. You're not saying what is the probability of 1.001, what is the probability of 1.002, what is the probability of 1.999, because each one of them would be 0. There is no possibility of 1.009 in a roll of a dice. So it is a uniform discrete distribution. It is not continuous. You cannot make a line here. That would be incorrect. Okay. So that is uniform and discrete. It's not continuous. Then how come we are saying that the ID variable outcome probability will become normally distributed? It is not normal. Yes, it will become normal. But right now, you're not dealing with sum or average. You're not dealing with sum or average. You're just dealing with one ID variable. Let's flip the experiment then and take two roll of a dice. So again, you're dealing with two ID variables. The two ID variables are the roll of dices. Now, first of all, let's try to find out the different possible outcome of the sum of the outcome of the roll of the dice. We know that the minimum possible value is what? 2. And what is the maximum possible value? 12. Why 2? Because the minimum possible value of each dice is what? 1. 1. So the minimum possible value is 2. What is the maximum possible value in each one of the dice? That is 6. So 6 plus 6, 12. So you have to find the probability of 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. These are the possible outcome of the sum of the roll of the dice. So let's find the probability of 2. How would 2 occur? 2 would only occur if you get 1 on the first die and this 1 on the second die. What is the probability of 1 on the first dice? It is 1 by 6. What is the probability of 1 in the second dice? It is 1 by 6. So what is the net probability? It is the probability of getting 1 in the first dice and 1 in the second dice. So what you're applying? You're applying AND rule, right? And what is AND rule? AND rule is a multiplication rule. So 1 by 6 into 1 by 6, that is 1 by 36. So you'll get 1 by 36 as a probability for 2 occurring. Okay. Now 3. Now 3 has two possibility. So 3 can occur in two different ways. 3 can occur in two different ways. 3 can occur if the first die gives an outcome of 1 and the second gives an outcome of 2. Or, I'm saying, or the first dice give you 2 and the second die give you 1. So I'm saying that what is the probability of 1 and 2? Apply the multiplication rule. 1 and 2, 1 by 6 into 1 by 6, that is 1 by 36. But that is probability of only one possibility, 1 and 2. Okay. What is the probability of 2 and 1? It is again, for 2 and 1, it is again 1 by 36, right? But we are saying, or either this can happen, which has a probability of 1 by 36, or this can happen, which has probability of 1 by 36. So you have to do 1 by 36 plus 1 by 36 because you have to apply or rule or addition rule. And because they are independent, you have to sum the probability of this and this. So 1 by 36 plus 1 by 36 will become 2 by 36. So two possible way, 2 by 36. Okay. Now, what about 4? 4 can occur in three possible way. If the first dice give you 1 and the second dice give you 3, or the first dice give you 3 and the second dice gives you 1, or the both the dice gives you 2. So again, the probability of each one of them is what? 1 by 36, 1 by 36, and 1 by 36. But again, you are saying either this will happen, or this will happen, or this will happen. So here you have to apply what? Or rule. So you add 1 by 36 plus 1 by 36 plus 1 by 36. So you will get 3 by 36. Similarly, for 5, you will get 4 by 36. For 6, you will get 5 by 36. For 7, you will get 6 by 36 because there are 4, 5, and 6 different possibilities. But something very interesting start happening from 8. The probability start declining. The probability of 8, instead of increasing, start decreasing and it becomes 5 by 36. The probability of 9 become 4 by 36. The probability of 10 become 3 by 36. The probability of 11 become 2 by 36. And probability of 12 become 1 by 36 for the obvious reason because there is only one possibility to achieve 12 when each one of the dice will have the number 6 appearing as an outcome. Okay. Now let's plot this. Now let's plot these probability against the outcome. Okay. Now something very weird start happening. Let's see. So let's first plot it. So probability of 2 is 1 by 36. Probability of 3 is 2 by 36. Probability of 4 is 3 by 36. Probability of 5 is 4 by 36. Probability of 6 is 5 by 36. Probability of 7 is 7 by 6 by 36. Probability of 8 is 5 by 36. Probability of 9 is 4 by 36. Probability of 10 is 3 by 36. Probability of 11 is 2 by 36. And probability of 12 is 1 by 36. So as you keep on plotting, a very weird thing start happening. A uniform discrete distribution, which was near to a flat line, kind of a flat line, is now getting converted into a bell-shaped curve. Not a proper bell-shaped curve, but appearing or will approach like a bell-shaped normal distribution. So actually what did we change? We changed only one thing. Instead of one individual ID variable, I started working with the sum of the outcome of the ID variable. Sum of the outcome of the ID variable. And as I introduce the sum of the ID variable, my uniform discrete distribution start getting converted into a bell-shaped curve. Into a bell-shaped curve. Definitely it is not normal distribution. Definitely it is not pure normal distribution. But understand, we have just satisfied two conditions, ID and sum or average. As we just increase the number of entity from 1 to 2, you start observing something like normal distribution. But what if n is greater than 30? What if you're not talking about 2 roll of a dice, but 30 roll of a dice? You'll start seeing all the properties of normal distribution. And that is the beauty of central limit theorem. Okay. So what we have seen? We have seen that when we take the sum or average, you could have taken average also. So instead of probability of here 2, 3, 4, 5, 6, 7, and 8, you could have taken 2 divided by 2, 3 divided by 2, 4 divided by 2, 5 divided by 2, or 12 divided by 2 because that is the average of the roll of 2 dice. You have to sum the number and divide by 2 and you will get the average. right? You can just play with the average. So whether you take sum or whether you take average, in the end, you are plotting the sum or average of ID variables. Then you will start seeing a normally distributed curve. Okay. And that's what we have observed here. And this is the introduction to the central limit theorem. And this was version 1. Version 1 is stating that this is one of the rationale for why you see normal distribution everywhere. So whenever you see the sum or average of a lot of numbers, and if the numbers are random, if the numbers are IID, independent and identical, you will start observing a normal distribution. You will start observing a bell-shaped curve. Not everywhere, but whenever you're working with sum or average of ID variable, you will start seeing a normally distributed curve if n is greater than 30. Okay. Now this was version 1 of central limit theorem. Now let's read version 2 for the central limit theorem. Yes, definitely will not discuss version 2 in this session, but I would urge you to read version 2 and try it to relate to version 1. So what is version 2? Version 2 says that for a simple random sample of size n from a population of mean mu and variance sigma square, the sampling distribution of the sample mean approaches normal distribution with a mean of mu and the variance of sigma square by n as the sample size become large, specifically greater than 30. So that is version 2. And in the next lecture, we'll try to discuss version 2 in depth. The reason for that is this is what is written in your curriculum for CFA and FRM examination. So we'll invest time in the version 2 as well. So we'll pause here and we'll meet in the next session of version 2 of the central limit theorem in the normal distribution lectures. Okay, with that, thank you. Have a nice day.